All right, let's take a look at some trigonal bipyramidal structures. Now, in this particular structure, I'm going to start at the beginning. Let's pretend there are no lone pairs. It's just your base geometry, and everything on the outside is exactly the same. Fluorine, 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 fluorine. Now, for this particular structure, your base geometry, where everything's the same, it is in fact nonpolar. There is no winner for those electrons. They don't get pulled towards one end of the molecule versus the other. Now let's explore why. If we look at this fluorine, it's pulling electrons towards it, up. There is a directly opposite pull going down. Those are going to cancel each other out. No pull on that situation. Then you have 3 fluorines that are all pulling exactly 120 degrees from one another. This is a 3-way tug of war in the middle. That is going to cancel out. That's basically a trigonal planar ring around the middle. So this pull will cancel out those 2 pulls. There's no pull ever overall as long as the atoms are the same, and therefore it is nonpolar. Now let's go ahead and add a lone pair. For this particular geometry, we don't want to put our lone pairs top and bottom in the axial position. Instead, we want to put it in the roomy equatorial position. If we go ahead and put one lone pair in the roomy equatorial position, top pull will cancel bottom pull. No problem there. However, the pull to the back does not cancel the pull slightly to the front. There is no counterbalance here. This is not symmetrical. If it's not symmetrical, there will be a winner. And overall, there will be a pull for electrons. And this is polar. One lone pair is always polar. Okay, let's do 2 lone pairs. Some people think if there's lone pairs at all, it's going to be polar. Well, that's just not the case. So let's go ahead and do 2 lone pairs. We're not going to do top and bottom. We're going to do the roomy equatorial position. So when I do a lone pair on the left and on the back and a lone pair on the front right here, let's look at what's left over. Top will cancel bottom. There's no pull. But there is nothing to cancel out the pull. If this had been like a fluorine and something else, there is nothing to cancel the pull of this fluorine to the left. Therefore, it's not symmetrical. Not symmetrical means there will be a winner for those electrons, and we are going to have an overall polar structure for this T-shaped molecule. Now let's go ahead and do the next variation. Let's say you had 5 domains and 3 of those were lone pairs. We're not going to do the axial top and bottom positions, but we're going to ghost out or lone pair the ones in the middle. Now, if we do that, something interesting happens. The top pull, if this was fluorine, cancels out the bottom pull. Let's all make them all fluorine. Those are going to cancel, no pull. And the 3 in the middle are all going to cancel out. This is symmetry here. The 2 lone pairs at 120 degrees from the other lone pair at 120 degrees are 3 all in the middle. The electrons that are in this direction pull the electrons in that direction and the electrons in that direction. We have a symmetrical molecule. There will be no winner. And even though we have lone pairs, that is non-polar. And again, if everything is on the outside is exactly the same, it's nonpolar. But if you replace just one of those with something different, let's say this is a chlorine and this is a fluorine. Well, no, then it's, again, not symmetric. Not symmetric means that it's a polar molecule. All right, we're going to go through the octahedral structures below, but I hope this is helping.